Hi, this is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we discussed about the basics of vibrations, and also in the last module we discussed about the basic isolation feature that you see when we are just trying to keep the isolator. Then what exactly the design strategies are there, or what exactly the procedure which we need to adopt to effectively control the vibration. And also then we discussed about mainly the vibration generation mechanism, in which various categories were discussed. And then you see here in the last lecture we discussed about the numerical problems. You see then when we are keeping even the vibration isolator, then how even the losses are being computed in that, how effectively we can produce the isolator at the specific location, or the amount of we can say the isolator properties, means you see the damper or the stiffness or the masses, how we can adopt those things. So, all these calculations were discussed in the last lecture, and we found that if you are just controlling the low frequency vibration or high frequency vibrations or at the resonant conditions, then how to choose the isolator. And the same time you see here we discussed about that you see even not only when the unbalance or any defective features are there in the component, then only the vibration generations are there. There are various other factors like the self excited vibration, like you see even when the things are being rotating and some air or some the flow induced features are being coming, then also you see here the system is excited. And sometimes even in the self excited vibration, sometimes you see the system itself is releasing the energy within that, and due to that, which we termed as the negative damping, the system almost becomes unstable. So, what I mean to say here, that there were various we can say the vibration generation mechanism which was discussed, right from material feature to we can say the masses, or even whatever the spring elements, and all these features are there. In this lecture now, we are going to discuss about the design considerations in the material selection, because when we are trying to say that we want to reduce the vibration right at the source, then certainly we need to choose specifically not only from the strength point of view about the material of the component, but also you see here that material should also provide some kind of damping towards the vibration excitation. Because you see here, if the material is in the support of the excitation, then certainly you see here along with the forcing frequency and all other factors, we may have some kind of the material phenomena, like you see some kind of which we discussed in the previous lectures about the negative damping and various various other features which will be coming out and contributing towards the vibration excitations. So, in the first category of the design consideration in material selection, the design sensitivity. So, we need to see that when we are designing something, then what exactly the sensitive parameters or the sensitive features of those the entire phenomena are, in which you see we need to consider in a very prominent way. So, in that, when we are talking about the large damping in any structural material, we know that either it is absolutely depending on whether the desirable or undesirable feature about the various excitation part. Because you see here when we are talking about all the structures and the bigger structures, we know that the material damping is always being coming out according to the property of material. So, sometimes you see here when we are talking about the desirable feature of the damping as far as the designer is concerned, then we need to see that how we can limit the peak stresses and how they can be extended to the fatigue life of structural element or any machine part. And in this case you see here we have to be very careful that when these excitations or any such kind of peak stresses are being forming, we need to limit which are very close to the resonant cyclic forces or even any kind of impact loading. When you see some abrupt changes are there, not only in the magnitude of the forces, but also in the direction where it is to be applied to the system. So, in that case it is the desirable property of a damping which is supposed to be there along with the material part, so that we can reduce the vibration excitation and the noise reduction both together. And even you see here, we can put some kind of obstruction for the transmission of these. While on the other hand, the damping is sometimes undesirable as well. Why? Because if some internal heating which we just want to avoid, then certainly you see, like if such kind of things are to be avoided, it is undesirable. And also we can say that when the damping is become the source of instability in any kind of rotating feature, then certainly you see here this is a kind of error generation in the sensitive instrumentation features. So when we are talking about the resonant vibration of the large amplitudes, which are always be there in many of the devices, then certainly you see here we need to specifically choose the kind of material which can provide an effective way for dissipation of the energy. And we know that some frequently causing, we can say like whatever the rough or the noisy operations, or even in the extreme cases when it is just going towards the high fatigue cycles or repeated stresses, then even also you see we can say that the damping is one of the specific feature. So there are various types of damping which can be employed to minimize these resonant vibration amplitudes, right from the intermolecular interactions, or even the structural features, or even whatever the fluid surface interface the interactions are there. So that interfacing, all these you see, either the fluid surface interfacing or even the intermolecular surface intermolecular arrangement of the material, they are all you see are just playing a critical role in putting the overall damping towards the system. So when we are talking about the design sensitivity, that means we are just talking about the effect of these parametric changes on the result of an optimum procedure, or even when we are just trying to change something in any of the design parameter in a system, we need to check it out that how these eigenvalues or eigenvectors are being changes and how we can compute those features along with the entire system performances. So in particular, if a design changes and which causes the system parameter to change, the eigen solution can be computed without having to recalculate the entire eigenvalue eigenvector set. And if this is there, we can say that whatever the changes are being there, it can be it is compatible and it can be immediately you see adopted accordingly. And this also you see referred to reanalysis process or procedure, and sometimes you see it is falling under the heading of structural modification. So we need to see that how the parametric variations or the changes in these like the whatever the parametric features are there are to be incorporated, so that we can just go for recalculation or reanalysis, and the things are supposed to be more effective in terms of the structural modification. So in this particular part, we need to again generate the equations according to whatever the changes, and in that you see here we need to discuss about the sensitivity of these changes on the natural frequency and the mode shape, means the eigenvalue and eigenvector set for any conservative system. So such kind of like studies which always like gives the kind of sensitivity are of more importance when you are designing a sophisticated element from the excitation features. And the modification for studying such method comes under the large order dynamical system often used in current vibration technology. So this is what you see, something which is a need of the recent time when we are going for the designing of the large structure. And we need to generate an efficient methodology, so that whatever the design changes are there, it can be immediately incorporated without having a significant change in the entire system. Just like you see here in the recent cars, what are the car modifications? Every year see these main car companies are changing their entire system. Like you see here, right from the combustion chamber to the entire engine features, even the braking system, even the steering features, even the power transmission features. And these changes right from the material to the entire structure, it is not that you see every time you will find that there is a significant change, but these minor changes are immediately it can be accommodated in such a way that it is not affecting the entire system, or it is not requiring the complete reanalysis and redesigning of the entire features. So, this is what you see the recent time requirement, and we need to go accordingly, so that we can simply adopt whatever the product designs are there, whatever the product like in the design procedures are there, or even the these production processes are there, it can be immediately accommodated. So, as far as the damping is concerned here, the two general types of units which are supposed to be specified in terms of the design properties of any structural material. The first, the energy dissipated per cycle in a structural element or the test specimen, and the second is the ratio of this energy, which is you see the dissipated energy, to the reference strain energy or the elastic energy. So, these two are the specific damping properties which has to be clearly specified in that way, especially for the structural membranes or the materials, in which you see we need to check it out that how much energy is to be dissipated in every cycle, and how you see the effect of this ratio which is in between the this dissipation energy and the strain energy or the elastic energy are to be disturbed with that. So, when we are talking about these two, first of all we need to go with what are the energy units which are available with the damping. So, sometimes we are saying that the total damping energy dissipated by the entire specimen in every cycle. Means when we are saying that like this is what the significant energy is being dissipated by the entire structural, which is a very common unit you see here. In general terms we are always specifying this, we are saying that this is D0, say the Newton meter per cycle, whatever the energy is being dissipated per unit cycle of the excitation of the vibration. Second, if we are saying no, we are not going with the damping, the total damping energy or which is being dissipated, we are going with the average damping energy, and average damping energy can be like calculated using the total damping energy which is being dissipated by the entire structural element divided by the volume of the entire specimen. So, in this case you see here we are basically looking for an average effect, because we know that sometimes like the moleculars are behaving in the nonlinear way. So, to go with the total energy dissipation from entire element is not giving the specific feature of that. So, in that case you see here we need to go with the average impact of such kind, and which is nothing but equals to the total damping energy of the entire structure divided by whatever the volume which is being occupied by this specimen. So, in that case we have the Newton meter divided by the meter cube per cycle, and we are saying this is dA. And also you see the third unit which can also be used sometime is the specific damping energy. That means you see here it has a very specific feature, when the work during the work you see here whatever the dissipations are there of that specific energy per unit volume in one cycle. But in this case you see here we need to take just like the stress or the force, that at a point how much specific energy is being released, the specific damping energy is being dissipated at that point in a unit cycle during that entire work part. So, at that point we can say that the specific damping energy D is nothing but equals to Newton meter again divided by the volume meter cube per unit cycle. So, these are the three damping features: D0, total damping, average damping dA, and specific damping D. And of all these you see here, we need to first go with the absolute damping energy unit, which is nothing but you see here the total energy D0 is always one of the specific part of the damping. So, as we discussed the three dampings, out of these three dampings, the absolute damping energy units, which simply showing the total energy D0, is the main interest of the engineers. And in that you see here the average damping energy, which we were discussing about, like the common features, is absolutely depending upon what the shape of the specimen, because you see ultimately our focus is on the volume, the entire volume which is to be considered. So, the shape of the specimen or the structural element, and also you see here it is just depending upon the nature of the stress distribution in it. Because you see sometimes when we are just talking about even the material is homogeneous and there is no the differences are there, but when you see when it is just subjected by the various stress distribution and whatever the heat formation is there with the structural elements or the intermolecular feature, and because of this the intermolecular dissipation, this intermolecular we can say whatever the oscillation, some kind of like the energy is being carried out and the material cannot be remain as the homogeneous one. So, when we are just going for our design part, and if we are just trying to focus on the average damping energy dA, then we need to not only check it about the shape, but also you see here that what exactly the type of or the nature of the stress is which is being distributed all across the material. And then also you see here it is also we need to check it out that when the material is subjected by the same stress distribution at the same temperature and the frequency, then what exactly the effect of these heat generations are. So, I mean to say that like when we are just going, we need to check it out not only about the shape or the distribution or the temperature effect, but also we need to see that whether it is convenient to take the average damping energy as the entire like damping property, or we need to go with the absolute energy damping. And when we are talking about the specific, the third one, it is the most fundamental of all three units, because you see here it depends only on the material, not on the shape or the stress distribution or the volume of any vibrating element. So, sometimes you see most of the methods which discussed you see here for measuring the damping property is just like getting the data on the total energy damping, that is the D0, rather than the specific damping energy D. So, you see sometimes like we need to check it out that why D0, why not D. So, like there should be a relation which should be like established in order to quantify these things with that assumptions. So, if we are saying that the specific damping energy D0 is just to be calculated for the entire element, then first of all we need to go with the D, that is the specific damping energy. So, D0 is nothing but equals to the volumetric like the volume integral 0 to V0 d into dV. And since it is a volume integral, so certainly it is a triple integral with dx, dy and dz, the changes in all three directions, and the d is nothing but the function of x, y, z, because you see here this is the specific damping and we know that it can be varied in all three x, y, z direction. So, we need to evaluate, if we are just going with the total damping, then we need to evaluate the variation of the specific damping in all three directions and needs to be computed altogether. And if these is the non-zero stress component, just like you see like in the stress, the tensor feature, then the specific damping energy D can also be considered as the function of this stress level which is to be distributed in all across x, y, z feature. So, by D0 the overall damping is the integral of 0 to sigma d, d which is you see like the specific damping into dV by d sigma into d sigma. So, now you see here we are just trying to multiply with the entire volume change and the change of this with respect to the stresses changes. So, in this integration we know that the V is the volume of material whose stress level is always being less than the sigma, and when we are talking about this we can say that the sigma d which is to be there is nothing but the peak stress, and these in these integrands which is just putting there. So, dd which is nothing but equals to the dimensionless feature of that is the specific damping and associated with the peak stress level, and which may be reached anywhere up to the specimen, up to the we can say when the extreme level of vibrations are there. That means, the d is nothing but equals to dd when your stress level is going up to the peak stress features, so the maximum stress. And when this is there, we can say that the d0 is nothing but equals to dd into V0, the original volume, into alpha, where alpha is nothing but equals to the coefficient which can be computed right from the integral 0 to 1 d by dd, the ratio of specific damping to the damping when it is reaches to the maximum value peak stress, into the variation of d v by v0 and d sigma by sigma d. So now this ratio is clearly showing the relation between the volume changes and the stress changes right from original to the peak value into like when we are computing d into d sigma by sigma d. So this alpha is a coefficient which incorporates all the type of variations, and then it is just like integrated those variation right from elemental level to the entire feature. And then you see with this part, when we multiplied with the dd, which is the peak stress, the damping at the peak stress into the original volume, we have the entire total dissipated energy. So the average damping energy in this case can be also formed as we discussed d0 by v0, and we know that it is nothing but equals to dd into alpha. The relationship between the damping energies like d0, dA and d is absolutely depending upon the dimensionless damping energy integral, that is alpha. So this damping energy integral is one of an specific property now through which we can directly correlate all three types of damping feature, and this integrand alpha can also be separated into two parts as we discussed. First, the damping function d by dd, which is simply the property of material, because you see here we can see simply that how the stresses are just going up to the peak level, accordingly dd is calculated and d is the specific feature. And also second, it is depending upon the volume stress function, because you see here it is also like related with the d v by v0 divided by d sigma by sigma d. So you see this alpha, which is one of the specific property for describing the entire damping feature of the material, which sometimes we are saying that this is something, the damping energy integral in the dimensional way is absolutely depending on both the part. So we can say that this is like the part which is depending on the shape of part as well as, because you see d by dd or the material property and the stress distribution in that. So both material property and the geometrical properties are straightaway incorporating in the alpha, and then based on this alpha we can like set up the relation in between these all the damping features. So like the several approaches which are being available for performing the sensitivity analysis for such kind, and in that you see here if we are just going with a parametric variation in the eigenvalue problem, now we can go with the n degrees of freedom system like say m into alpha, which is like the whatever the mass features are there of the material, m into alpha q double dot t plus k alpha, which is also the property of this alpha qt equals to 0, where we are just trying to show the dependence of these mass or stiffness matrices on the coefficient matrix of these like we can say whatever these we can say either the mass matrix in which the coefficients are there, the stiffness matrix the coefficients are there, just depending on one design parameter alpha, which is nothing but equals to the like just showing the relation of the damping in all sort. And this parameter alpha is considered to represent the change in matrix either m or k in such a way that like whatever the changes are there in the material or in the shape, it can be immediately incorporated in that. So when we are trying to relate this with our eigenvalue problem, then we know that we need to go with the inverse part. So m inverse alpha into k alpha u alpha is nothing but equals to my eigenvalue lambda I alpha into ui, that is my eigenvector. So when we are trying to relate these things, then we can say that we can easily find out the eigenvalue or eigenvector means the lambda I and ui like based on the variation of the alpha with related in relation to the mass and the stiffness matrix. So this mathematical like discussion or whatever you see like the dependence feature of this entire mass and stiffness matrices on that is being described by the visual, and then you see in this we simply find out that when we are just trying to calculate the eigenvalue and eigenvector, straightway we need to just go with the double differential features to calculate the alpha in that. And when we are trying to do this, you see here, we could easily figure out the eigenvector ui alpha, which can be normalized using this, like the mass matrix with differentiation of these, the entire feature with respect to this alpha. So in that, the d lambda by d alpha, because we want to differentiate it out, this is nothing but equals to whatever the transpose feature of my eigenvector means, like the ui transpose into dk by d alpha minus lambda I dm by d alpha with respect to ui. So both the differentiations are being there with the stiffness and mass matrices, and they are absolutely depending on the alpha. So delta alpha is one of the design parameter, and it's clearly showing that if any changes are there, the entire changes are there not only in the eigenvalue but also in the eigenvectors. So it simply shows the sensitivity. So if we are going with the double derivative of this lambda in the differentiation feature, because we want to calculate those things, so it is nothing but equals to d2 lambda by d alpha square equals to 2 u dash transpose dk by d alpha minus lambda into dm by d alpha, that was there, plus now u transpose d2k by d alpha square minus d lambda d alpha dm d alpha minus lambda I d2m by d alpha square. So this is what a clear variation in the stiffness and mass matrices when we are going for the double derivative feature of the lambda with respect to the alpha. And this, you see, the u dash, which is simply like we are keeping there, is nothing but the derivative of my eigenvectors with respect to the u. So we can say that the second derivative of this, like the lambda, is simply showing the dependence of the, like all the stiffness and this mass matrices on the lambda, and this is clearly showing that the requirement of the existence and the computation derivative is absolutely showing the eigenvector variation in the double derivative. And where you see, like when we are saying that the m is constant, then certainly the eigenvalue, the eigenvector derivative can straightway coming out with straight, with this particular formula, where the dvi by d alpha is nothing but equals to summation of all these variation right from 1 to n c, which is again, you see here the coefficient is there in that, absolutely like depending on the eigen value, and with the associated, you see the matrices. So c, which is I comma alpha vk, and vk is absolutely, you see, the vectors which is based on the mass transformation. So we can say that we can calculate vk as mi divided by 2 uk, and ck can be, because the ck is depending on the I comma alpha. So we can say that it is when I and k both are same, means when there is no variation in that, certainly it is 0. So whatever the variations are there of dvi at d alpha, it becomes 0. But when you see they are not equal, then certainly it is showing a difference in the lambda value, lambda I and lambda k, and then you see we can straightway calculate by 1 by lambda I minus lambda k u of transpose dA by d alpha ui. So the coefficient can be straightway calculated according to what the variations are there, and then you see we can say that the matrix A, which is just showing the symmetric matrix there, is absolutely depending on A, and the symmetric matrix is m to the power minus half k m to the power minus half. So you see here, this is what the symmetricity in between the stiffness and mass matrices, and accordingly we can calculate the entire features. So when we just want to calculate the sensitivity of the eigenvector and the eigenvalue for any conservative systems, then we need to go that whatever the changes are there in the stiffness matrices, and then we accordingly we can simply find out the overall effect on these part. So we can say that when we are just going with computationally efficient methods for the sensitivity, we need to go and adopted various things. In the recent paper of Adhikari, they are also calculated all these sensitivity for the damped system, and they simply shows that how these mass and the stiffness matrices are depending on these design parameters. So when we are talking about the design of damping, there are various ways through which we can calculate. Like you see, we can take the laminated material, in which you see some laminated metals are there, and they are being simply putting for effective and control of this one. And this laminated metal material offers an effective way to increase the inherent level of damping in a simple sheet metal for vibration transmission and the generation. So, sometimes they are assisting to the product engineer with consideration of these, like the laminated material in place of the traditional sheet, and then we need to check it out that how we can optimize the damping with this, then how we can go with the this laminated features, and then how we can make the entire composite part. So, this optimization of the laminated construction is absolutely requiring what the parameters which are being required and how it is being added to the base material, so that it can provide some kind of viscoelastic material property or other material property. But again, you see, this kind of feature is always offering a complex solution, and you see here like the design flexibility, like you see in the previous case we have seen that just a design parameter is there and sensitivity of the entire feature is depending on that. But here you see here we need to check it out for such kind of thing, that what is the thickness or the type of like the damping cores are there, or even like what are the constraining layers are there, which has to be put in such a way that we can get an optimum effectiveness of this product. So, there are various approaches are being available in that. According to, we can simply select and design the viscoelastic based damping treatment of such problem. So, the first is the RKU approach. The RKU approach is nothing but you see like the three scientists, they simply offered this, the Ross, Kerwin and Unger, and they said that we can simply go with the real world component and we can straightway make an equivalent 3-layer beam or the plate for such systems. So, they suggested the method uses simply a 4th order differential equation for this uniform beam, which has like sandwich kind of sandwich kind of feature in the like in this 3-layer laminated system, and they simply replace this 3-layer laminated feature with the equivalent complex stiffness. So, in that the basic impact is coming on the flexural rigidity EI, because sometimes you see here like we cannot simply replace this EI, because E is the Young's modulus, the I is the cross sectional feature. So, both material and the cross sectional features for these like the equivalence feature of the 3-layer laminated part is somewhat more complex, because you see here when you are just going in a uniform way, it is pretty easy to put in a linear algebraic way that just put in added those part E1, E2, E3, or you see I1, I2, I3 added and we can get. No, it is not like that, because the real world problems are somewhat different. So, we need to make certain assumptions when we are just going with the mold shapes of this structure, because we need to see that when it is a sinusoidal nature, then there is no problem with such kind of boundary condition like simply supported or this. But when you see some kind of nonlinearities are there in that deviation, then we cannot go with the strict linear assumptions. So, first with this approach, the other boundary conditions which are necessary in the working with the actual we can say structure, the approximation which has to be there according to the mode shape in this part. So, RKU method is really good as a damping indicator when simply we are not going for the precise damping, but we are just going with like some kind of formation for the real complex part. And the goal is to use this simplified method to develop the design train. We will simply give a selection of damping material with the constraint layers, the thickness, and just to adopt these things to provide you see here the optimum damping procedure. So, this was the first approach. The second approach is the modal strain energy. So, the method which is based on the modal strain energy is being utilized for the finite element solution of such problems, in which you see here the entire element is discretized based on you see here various molecules, and then this method is just providing an accurate predictor of the damping level, which is simply comprises of the various layers with the properties of elastic and viscoelastic elements. So, this principle states that the ratio of composite system loss factor, because you see we know that when we are talking about like the viscoelastic feature, there is always a loss factor is there. So, the principle here states that the ratio of the composite system loss factor to the viscoelastic material loss factor for a given mode of vibration can be simply estimated with the ratio of elastic strain energy in the viscoelastic element to the total strain energy in the model for a given mode. So, this is one of the significant feature of this like the strain energy based principle, that we can straightway go to the elastic strain energy in any viscoelastic element, and then what is the total strain energy is there in the entire model. So, when we just want to show mathematically, then we need to simply go with certain equations which simply consist the MSE approach in some conjunction of the undamped normal model analysis, which simply gives you the strain energy ratio in that. So, the strain energies can be determined in relation to the mode shape, relative mode shape, and it is being assumed that the viscoelastic properties here are somewhat linear in terms of the dynamic strain rate. So, when it is linear, then we can say that the neta S to m, that is you see the that is nothing but the viscosity, is the NVM into UM Vm divided by UM total, where we know that this neta is nothing but the damping for the nth mode of the structure, and NVM is nothing but the material damping for an appropriate frequency and temperature, and Vm into m to the power m is nothing but the elastic strain energy stored in the viscoelastic core, and n total is the total strain energy for nth mode shape. So, we can straightway relate the system damping with respect to the material damping at a certain temperature and frequency, the elastic strain energy of the viscoelastic core, and the total strain energy for nth part. So, now you see lastly we are taking one example in which you see here we are simply considering that we have the mass m, which is like the same example which we discussed in the last chapter, the last numerical was there. We have the stiffness matrix K is 3 minus 1 minus 1 3, so that you see the inverse and this becomes same. So, we can calculate the eigenvalue for such undamped system. So, it is lambda 1 comma 2 is 2 comma 4, and the normalized eigenvector can also be calculated as u1 is nothing but equals to v1, and we have 1 by root 2 1 comma 1 transpose. So, u1 and u2, v1 and v2 can be calculated, and it is desirable to compute the sensitivity based on the natural frequency and mode shape as one of the parametric changes of that. So, now you see here for this, now we are just taking the stiffness matrix based on the sensitive parameter, say A. So, we are adding 3 plus alpha, this is what my design parameter, 3 plus alpha minus 1 1 comma 3. So, we can simply see the mass and stiffness matrix with the variation of alpha, we can get you see like this 0 0 0 0 mass, and stiffness you see 1 0 0 0. And when we are keeping these things, now we can get the derivatives of the eigenvalue and eigenvectors, the d lambda by d alpha, d lambda 1 or lambda 2 both with that, and also we can calculate d u1 and d u2 with respect to alpha in this way. And once we calculate these quantities are clearly showing the sensitivity of your eigenvalue, means eigenvector and eigenvalue problem based on whatever the changes are there in the stiffness matrices. So, correspondingly you see we can straightway put those things to get the final value of lambda 1 alpha and lambda and u1 alpha, like lambda 1 alpha is 2 plus 0.5 alpha and lambda 2 is 4 plus 0.5 alpha. So, you see whatever the changes are there in the alpha, corresponding changes are there in the eigenvalue or the natural frequency. Similarly, we can get the u1 alpha and u2 alpha proportionate. So, it is nothing but equals to 0.707, the square root is there. So, 1 comma 1 plus 0.177 alpha minus 1 comma 1, and similarly we can get the value of u2. So, in this numerical problem you see here, we could easily find out that when we are trying to get the eigenvalue and eigenvector for that, whatever the changes are there in the parameter can be immediately put without changing in the entire system features. And these formula can simply give some kind of the reanalysis feature only, not redesigning feature. So, we can say that the sensitivity in terms of percentage can also be calculated like lambda 1 alpha minus lambda 2, lambda 1 alpha minus lambda 1 divided by lambda 1. So, it is giving 25% of this part alpha. in terms of lambda 1. So, if the changes in the system is small, say alpha equals to 0.1 or something, then eigenvalue changes are 2.5%, and eigenvalue lambda 2 is also being changed by 1.25%. On other hand, you see we can go with the eigenvector, that is also being changed by 2.5%. So, in this case we can say that we can straightway calculate that eigenvector which needs the change in percentage is 2.5% more than that, is more sensitive towards the design parameter as compared to the eigenvalue. So, we can say that the relative displacement in the entire structure when we are changing any this alpha or that kind of feature is become more significant as compared to the exciting frequency. So, in this numerical you see here we could figure out that what the lambda means the eigenvalue and eigenvector are absolutely depending on this this design parameter, and we can see the changes in that as we are simply changing the design parameter changes. So, you see with the using of this approximation matrix composition, the equations for eigenvalues and eigenvectors can be again remodified according to the changes in that, and you see here these multiplications or the manipulations can be done as per our requirement, as per the applications and as per the conditions, the constraints which are being available according to the sensitivity analysis. So, in this chapter we discussed mainly about the sensitivity analysis in this, which has you see a significant part on not only on the eigenvector and eigenvalue based, but also you see here whatever the damping features are there in that, how do we calculate the overall damping feature, which parameter will give you the real reflection of that, and in that even in the damping what exactly the sensitive features are there, not only right from the material chosen but also from the application part in that, and what exactly the excitation features are there. So, if the design of the system is concerned with the avoiding resonance, then we need to see that how the frequencies are being shifted according to the stiffness, and then you see here what exactly the critical parameter is there which we can choose as the design parameter to see the effect on the eigenvalue and the eigenvector. So, this was the first part of the design of the material chosen or the material consideration based on the sensitivity analysis. In the next part you see here again we are just trying to see the design of the material selection, means what exactly the design concept is there for the material selection just to suppress the vibration when it is being excited. So, there are a lot more parameters are there which we are going to consider for design of or for consideration of the material selection based on some design features. Thank you.